Thanks a lot for inviting me to deliver a talk here. I will speak about algebra, which from my point of view is very remarkable. And I will try to convince you that it is so. So I would like to mention that Saponov is my colleague since long ago. Zaitsev is his student. So very brilliant student. So I would like to explain my special interest to this algebra, in this algebra. So this algebra is looking like the enveloping algebra UGLN. And this algebra has many properties similar to properties of this algebra, in particular the representation theory. However, the traces centering all corresponding representation of this algebra should be different, traces should be different from the classical one and should be coordinated with the gradient which comes in the definition of this algebra. Simplest example of this algebra is super algebra here in super algebra PMN. It is just a notation for supertransposition of two elements. And trace here is also deformed. It is deformed in sense that it is super trace. It is not the usual trace. Okay, now I consider the space V over the field C, and I consider invertible operator R acting from the square root in the same space, satisfying the so-called Yang-Baxter. It is not Yang-Baxter equation. I call this relation Braid relation. And identity here is identity operator. And if R is equal to P, P is, I use this notation for the usual flipper. We have as an example of this, super flips are examples of this, and but with examples are subject to the relation R squared is equal to identity. Such braiding are called involutive symmetry. But more interesting are the so-called Heike symmetries. Heike symmetries are braidings which are subject to the following condition. Q is assumed to generic. And if we have R, we denote by RK operator which is put in the position K plus 1. Here and here identities. Now, I would like to mention that finally this picture is a representation of the so-called braiding Artin braid group. So you know the Artin braid group is generated by tau 1 and so on, and identity, of course. And the relation are similar. So if distance between two elements is 2 or more, so they commute. This relation is just braid relation. And if we impose one condition more, so we call this condition Heike condition, we have Heike or Ivachori-Heike algebras. And as I said, Q is assumed to be generic. Okay, I present here to the most known example. The most known example are coming from the quantum group of Drinfeld, and another example is deformation of supertransposition. If you put here Q equal to 1, you have here the matrix of the usual flip, and here the matrix of superflip. Okay, now it is very natural to introduce the generating series. I call them Hilbert-Poincaré series, define it as follows. So this is analog of symmetric algebra, this is analog of skew-symmetric algebra. I would like to say that from physical point of view, elements of this algebra are analog of boson, and elements of this algebra can be called Q fermion, as you wish. So I consider the corresponding Poincaré-Hilbert series, and as usual, with K stands here for the homogeneous components. Okay, now I present here some examples. For the usual flip, we have the following Poincare-Hilbert series. Here we have Poincare-Hilbert series for super flip PMN. And many years ago, I constructed many examples which the following Poincare series. So N can be very, very big. If P minus is polynomial, I is called even, so in general sense, of course. But in general, with function is rational functions. And if we have this situation, we have the polynomial of degree m, degree n here, and in general, if S are just incancellable fraction, and I is degree of the polynomials here, and S is degree of polynomials here, I call this couple S just be rank of R. And finally, many quantities can be expressed via B rank. Many quantities, physical in some sense. Now, I repeat that we have here generalized boson and fermions elements, and my next step is to explain what is bosonization of algebra by with boson and fermion. Bosonization and fermionization. So if we consider the examples enveloping algebra of GLN, and LAJ is just a generator with algebra, so bosonization looks like that. So here we have the A basis is in space V. Here we have basis in the dual space. And finally, if I have here dual space, right dual basis rather, we have the following coupling between two elements. But if we change the order, so if we put xj here, it is completely different. The problem is that in generalized situation, just like classical situation, the order matters. Here, the classical coupling, here it is not classical coupling. So I denote with coupling by Bij. I consider the corresponding matrix with matrices n times n. And finally, I would like to say that this matrix is completely determined by A, by initial braiding. All this stuff is valid for any braiding. But in classical situation, if I is equal to usual flip, B is equal to identity, 1. In a super case, we have here 1, 1, 1, after that minus 1, and so on. But in general, B has not be even diagonal. So in general, it can be very, very general. But what is type of with generality, I cannot say. I can construct many examples where it is not diagonal, but this problem is difficult. I would like to note that with matrix B is subject to this relation, and this relation is just a representation of this so-called RTT algebra. Because you see RT1, T2, it is just a relation, is the algebra considered in Leningrad Mathematical School by Drillfeld as well. Okay, but now I want to introduce our main actor. It is just reflection equation algebra. I take R, and almost any R can be used here. And L1, as usual, is the matrix L composed from entries Lyj multiplied by identity. And with algebra, it's very it's necessary, of course, to check that this algebra is well defined. So the dimensions of matrix are good. And finally, it's possible to compose with relation. And with relation differ a little bit from this one, because here we have 0 in the right-hand side, and here we have linear term. On the left-hand side, we have quadratic terms, and here we have linear terms. I denote with algebra in the same way, but harder. here. So LX hatted. And we call it modified reflection equation algebra. Okay, now it is not the classical situation. The classical situation, you know well, that symmetric algebra, which is a limit of reflection equation algebra when R is going to P, the usual flipper, as Q is equal to 1. As modified reflection equation algebra tends to the enveloping algebra, and with algebra are not isomorphic to each one. And finally, here, by this change, it's possible to go from the reflection equation algebra to modified reflection equation algebra, in spite of the fact that in the limit Q equal to 1, it is not possible to do. Okay, but I would like to say that many properties of this algebra looks like the properties of the enveloping algebra. Okay, now I consider an example with R equal to P. We have the corresponding algebra as follows. It is just a definition relation for symmetric algebra, and similar here, apart from the right-hand side, it is just the algebra describing the enveloping algebra GLN. It is not well known with writing, but it is so. You can check that it is just commutative algebra, and this is not commutative, but enveloping algebra. Okay, so I say once more that with algebra and with 1 are analog of these two algebra, with algebra and with 1. But now our next aim is to introduce analog of symmetric polynomial in these two algebras. It is not so easy to do. But in principle, if we know what is a Q analog, quantum analog of the tracer, at R trace, I call with trace R tracer of any matrix M. It is just the usual trace, but here appears the matrix C. The matrix C is completely defined by R. So how is possible to construct the matrix C if we have R? It is not so easy to explain. But what we need the property of this tracer. If we consider the matrix L in power case, after that we apply the R tracer to this element, to this matrix, we have here matrix. We have element which belongs to the center of the corresponding modified, here modified reflection equation and here non-modified reflection equation. And I would like to note that this matrix C, the matrix B presented above, they are related by this relation, where R and C, S are just by rank. Что там шумит все время? So we have this relation. It is not so easy to get this relation. So the matrix B and C are almost inverse one to other. Okay, now I want to construct the center. And in order to construct the center, I introduce the following notation. L1 over line, it is just L1, so here no modification to do. L2 over line, it is just L1, and here instead of the usual flip, we put R, and so on and so on. So it is pushing from one position to the next one by matrix R instead of the usual P, which usually is used in this situation. After that, I consider the following chain of the matrix L1 over line, and so on and so on. And now, example, if L is 2 by 2 matrix, L1 over line to L1 without overlining, we have the following matrix, and after that we put I at R minus 1 in this position. Now, the very important statement. This statement belonged to Isaev Pyatov, maybe it was before that, but finally I know this statement from the paper by Isaev and Pyatov. If we put here any element belonging to Hecke algebra, Z. If we apply this element via a matrix representation, it means that instead of generated tau, we consider the corresponding images are in position 1, 2, and so on and so on. And after that, I put here the chain presented on the previous page. We have element which is central in this algebra. So it is a very important step in construction below. So you see our matrix representation is just we send the generator of Hecke algebra to our matrix which is located in position k plus 1. And the map sending the element of the Iwahori Hecke algebra to the element of reflection equation algebra is called characteristic. And finally, hopefully, the image of this map coincide with center. So hopefully, all elements of the center can be presented in this way, but it is not shown. But finally, it's very plausible. Now, so on the previous page, I described what are power sums in this topic. So power sums are central element here because it's possible to present power sums in the way presented on the previous page. And what about other symmetric function, analog of course of symmetric functions? I consider here Schur polynomial of functions of this algebra. So it is constructed with element Schur polynomial is constructed in the same way, but here Z is projector corresponding to the representation of Hecke algebra. So in the theory representation of Hecke algebra, there are some elements E lambda yy, and finally it's necessary to put this element here, and it is good definition of Schur polynomial in this topic, in this algebra. Why it is so? It is not evident for the moment, because you know what is quantum polynomials, quantum Schur polynomials. Quantum Schur polynomials were introduced by many people, for example, Anatoly Kirillov, and finally, but it is another topic in another setting. Here, I present you quantum symmetric polynomial related to reflection equation algebra. And for me, the most interesting property of this algebra is that in this algebra, the trace is deformed. It is not classical trace. If you use here in this construction the usual trace, it doesn't go. Okay, now, what is Frobenius theory in our setting? First, in the classical setting, with relation, finally. Here we put the usual symmetric polynomial power sums, here the usual Schur functions, and passage from one set to another set. It is just coefficients which are representation of symmetric group, representation labeled by lambda, and evaluated on elements of Sackley type nu. But in Q situation, in our braided situation, it's similar. But here, chi is just character of representation of Hecke algebra. I don't want to go into detail. It's necessary much time. But finally, I would like to say that Arum Ram proved a similar formula, but only for R coming from quantum group. So with this publication of 90s, finally we consider our paper as a generalization of Arum Ram result. Okay, but I would like to say that in our approach, we use more or less MIVA approach to presenting quantum symmetric functions, because we are dealing for the moment with matrices. And now I want to introduce what are eigenvalues of these matrices. The matrices are now composed of commutative entries. In now non-commutative situation, it's necessary to define what are the eigenvalues of these matrices. And they are defined as follows. The matrix entering which comes in the definition of reflection equation algebra is subject to Cayley-Hamilton identity. With Cayley-Hamilton identity is valid provided I is even, or the B rank M0. So we're dealing here with boson. And in a more general situation with fermion, Cayley-Hamilton identity became more general, more difficult, more complicated. And if we apply here trace, good trace, of course, A trace, we have the relation which is called Newton identities. And finally, we can express one family of quantum symmetric function via the other one. And you see, if you take the book by MacDonald, in this book there are some formula where power sums are explicitly expressed via elementary symmetric function and vice versa. So you see in our situation, in Q situation, we have the following formula, which coincides with formula from book by MacDonald for Q equal to 1. So it's possible to express one family through the other one. And here similar, but instead of elementary symmetric function, we have here full symmetric function. And two families, elementary and full symmetric function, are particular cases of sure symmetric functions. And now I would like to say that bosonization, what I spoke about a little bit above, gives us a possibility to introduce pairing on the space of generator of the envelope of the reflection, or rather modified reflection equation or non-modified reflection equation. It is more or less similar. But if we want to deal with situations similar to enveloping algebra, we take two elements from the modified reflection equation algebra, we apply bosonization to this element with one, we have the following product here, and finally after that we apply coupling. If we apply coupling here, we have B, it is not delta, but here the order is good. The dual space on the right with coupling with this, it is just delta. And you see, we obtain it. An analog of the enveloping algebra GLN. And we obtain it at analog of pairing. So maybe it is more or less reasonable to try to use this stuff to define an analog of Vasilyev invariant in the sense of Kontsevich approach. What is a Kontsevich approach in this setting? So we have, so now it is for me more easily to present this by using another more developed approach by some people. Finally, we take any element of symmetric group, is a transposition, some transposition of elements, and we put here we consider the following sum. So to any element of Sn, we assign this element. And finally, it is not difficult to see that the element belongs to the center of the enveloping algebra. Here, Lyj are the standard generator of this algebra. And now, we get this element belonging to the center of an enveloping algebra, and after that one usually apply Harry-Chandra map to this element. Why? Because we want to have the answer, the final element belonging to commutative algebra. And commutative algebra is nothing but the Cartan algebra of this enveloping algebra. That's all. And recently one student of Landau generalized this stuff stuff to the enveloping algebra of the superalgebra of this type, it is not so difficult to do. But I would like to say that the idea to generalize all this stuff to braided algebra, which I consider, was for the first time considered by Weintraub, but he considered only involutive symmetry. It is not so interesting. Moreover, it was not clear what is an analog of Harris-Chandra map in this situation. And so now, I would like to explain what is good analog of Harris-Chandra map. So you see, okay. So you see, I consider here an example, following example. I consider sigma as follows. 1 is equal to 3 and so on. After that, I consider the classical situation, so covered by approach by Maxim. So we took here L1 hat, it is matrix. Here we put the element transposition, flip, the usual flip. 1 it means 1, 2. 2 means 2, 3, and so on. After that, we get an element belonging to the center. After that, we apply Harris-Chandra map. But if I want to apply all this stuff in a braided situation, in Q situation, we proceed in the same way. But here, L hat are matrices generating the generalized reflection equation algebra. The usual flip are replaced by R, and so on and so on. And if we consider the following element, we have the following result. You see, here I use this notation. You see that if we proceed in this way in Q situation, where I use this notation for trace of the matrix, by good trace, A trace, we have the following answer. It differs from the classical one. For Q equal 1, we have just with term disappearing. Okay, but the problem is, it is not yet verified what is Q analog of Q term coming in this stuff. Because in order to get Vassiliev invariant, it's necessary to have some relation between some diagram. It is not clear for the moment. But now I want to explain what is eigenvalues in our stuff. We introduce mu roots of the Cayley-Hamilton identity. Cayley-Hamilton identity, and here the first coefficient, second coefficient, and so on and so on. And because all coefficients here are central, we have here central extension of our algebra. Of course, we assume that mu are central in extended algebra. But if we have not even case, if we have case in general case, if we have Berank Mn, we have two sets of eigenvalues, even eigenvalues and odd eigenvalues. We have the following parameterization via the eigenvalues mu and nu for power sums, where coefficients here are as follows. If we put here Q equal to 1, we have the following formula, which is well known for supercase. But I would like to note that these polynomials are just whole little root polynomials. In even situation, it is almost whole little root polynomials up to this factor and up to this notation, because in the book by McDonald's, Q in power minus 2, it is just the parameter T. Okay, now I want to say that whole little root polynomials appeared in the integrable system in many topics, but only for the parameter t is equal to -1. In this situation, the Q analog of Q sure functions, rather, which are useful for defining B Kadamtsov-Petrashvili hierarchy. And finally, what is problem in general situation? Why in this situation t equal to 1? In our situation, it means that q minus q is equal to -1, so q is equal to e, y, but doesn't matter. Finally, it's possible in this situation to deal with usual derivatives. In our situation, it is not so. So in our situation, what is derivative in the generator Lyj? It is not so evident. But we succeeded to define what are derivatives in the generators of our algebra by using the language of quantum dual. And finally, it is just Q generalization of Heisenberg algebras. But after defining quantum derivative in this generator, it's possible to try to do next step. But it is not, for the moment, it is not so evident. I would like to say that in classical situation, one uses the following formula well known, which is called Cauchy formula. But in our situation, this formula fails. So how is relation between the two families? It is just relation presented above. It is just determinant formula or Newton formulas, and so on and so on. In classical situation, we have a Jacobi-Trudi formula. A Jacobi-Trudi formula is valid in our situation as well. And instead of this relation, instead of Cauchy relation, we have the following one. But here, attention please, here the following series as follows. Here it's necessary to put the following factor, q minus 1. So it differs from classical situation. And
is E?
Here?
Вверху А написано.
Yes, sorry. A and E, it is the same. Okay, so so now what 5 minutes. 5 minutes? What I want to discuss to complete my communication. Finally, I want to consider if we know a way to generalize the notion of partial derivative, it's very natural to consider an analog of partial differential operator. And for example, I want to explain what is an analog of the so-called cut-adjoint operator. A cut-adjoint operator, whose name was introduced by Gould and Jackson, but finally studied by Morozov, Mironov, and so on. And finally, now it is rather called W operation. But what is in classical situation cut-adjoint operator or W operator? You see, we have L, the generating matrix of this algebra. This algebra in classical case is commutative. D composed from partial derivative. If we consider the product of these two matrices, we have just a generating matrix on the envelope algebra. It is classical result, and moreover, the generator here are presented by an analog of Euler vector fields. But if we pass to the situation, Q situation, we have more or less similar statement. L is generating matrix of reflection equation algebra. D is composed of partial derivative mentioned above, but without explanation. And finally, the statement is L hat is just generating matrix of modified reflection equation algebra. It is a very important algebra for the other study. And finally, now, what are cut-adjoint operators? They are defined as follows. Here we put, I consider a Q case. general case. Here we put here power sums, and after that we put 2 points. It means that I consider ordered Casimir operator. And what is ordered Casimir operator? You know that in classical situation, if we have the following relation between partial derivative and the element L, we have the following relation, but if we omit with terms, constant terms, we have the following transposition. In similar way, we proceed in our Q situation. And in this way, we get the so-called normally ordered Casimir operator. And finally, in this way, we obtained quantum analog of some result belonging to Okounkov. We have quantum matrix Capelli identity as follows. Here P is just the following fraction, and J is the so-called Euclid's-Murphy elements. I don't want to explain what does it mean, but I would like only to say that at paper by Okounkov there is a classical analog of this relation. So now I would like to mention a paper by Perelomov-Popov, classical paper, which computed what is value of Casimir operator in a reducible representation. Reducible representation of the enveloping algebra are labeled by partitions. And if we consider the central element, you have the following image is a scalar of the following type. And finally, I present the result by Perelomov-Popov as follows in 2 steps. So Casimir can be presented in the following way, where M hat is just given by the following formula. So the 2 steps means that we have the following parameterization via eigenvalues. How it's necessary to define eigenvalues, I explain all this stuff. And image of the roots of eigenvalues is presented by the following formula. In our Q situation, we have similar. In even situation, for even R, we have the Kelly-Hamilton identity. We introduce mu, as explained above, and we have the following formula. So first we have presented we have the following value for the roots or eigenvalues mu hat in the representation labeled by lambda. And finally, with relation, I speak still of classical situation. So it is second step of Popov-Perelomov construction. In Q situation, we have the following parameterization. If we have the following value or character, as you wish, of mu. So it is generalization of Popov-Perelomov construction. And if we apply with change of the matrix, we have the following parameterization for Casimir and character for mu as follows. And by passing to limit q equal 1, we have just the Perelomov-Popov formula. So I would like to stop here.
Thank you.
So I have only one remark that some times ago we with Roland Speicher considered situation with your young Baxter operator was very simple. Q times identity, not identity, but Q times. Did we also treat because we would take more symmetric? Yeah, we only consider very simple exam, and then comes to Kunz algebra and new Neumann algebra, tra la la la. But only some case but you understand you are more symmetric situation. Yeah? So your Young Baxter is not such similar Q times identity.
But
Q times twist. So sorry, Q times twist. Q times twist. Yeah.
Q times twist. Okay. But finally, if you consider Q time twist, so you have R, which are equal Q P. Okay. P, if we present this by matrix, we have Q, 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 Q. Do you agree? And finally, the question: what is corresponding symmetric algebra or Q-symmetric algebra? It's necessary to take two elements, to transpose them by using this, and you have Q, X, Y, X, Z. So you can consider this transposition as follows.
That exactly, and then we come to Voronovich quantum group SUQ.
But I would like to say that there exist two matrices. One matrix was presented above, and another matrix is as follows. No, 1, 1, Q, Q minus 1 rather. So for them, for these two matrices, the corresponding symmetric algebra is similar, similar. Symmetric algebra corresponding to the same. But if you consider Q-symmetric algebra, they are not similar. So this example is not very interesting, because it's necessary to consider two algebra boson and fermion simultaneously.
Also, because when Q is 1 is boson, when Q is minus 1 is fermionic. This is that for us interesting.
I understand, but finally it's necessary to consider for fixed Q two algebra simultaneously, for me.
Okay, so I like and thank you for your exposition, and now we will Speicher think about your, because we don't know your papers before. We worked 30 years ago, so you know, probably you don't teach our business. We are related to Kunz algebra or Kunz-Krieger algebra. This was that business. Yeah. Anyway, but this now is new effect, and of course I always remember Sergei Kirov, asymptotic representation, when he more or less works maybe similar way, but not such abstract. Yeah.
If you consider Q analog of torus, what is Q analog of torus? It is xy is equal qyx. Okay? Okay. With this information, it's not sufficient for me, because as you put with a relation, you have analog, Q analog of boson. But what is Q analog of fermion? It is not clear. And finally, you have some freedom for constructed fermions.
Okay, I agree
with this problem. Sure that you have right. And I would like to finish this following remark. I know some papers where with factor that the corresponding fermion algebra is not defined uniquely, was published a number of papers, and with paper were wrong. False.
Good point to for next talk. Thank you.